Thank you. As Sami said before, I recently finished my PhD at MPS. So now I am a postdoc here, and I work on Starspots, and I mostly work on the radiative MHD parts. And recently, I have been focusing on also on synthesizing spectral lines and studying the impact that spots can have on the radial velocity of a star. So why be interested in star spots at all? So for me, the most interesting thing about spots is that they're the best examples of the interaction of magnetic fields and convection. So there's a small animated GIF here, which of a sunspot that I simulated in a slab geometry, and you can see that even the umbra is quite dynamic and not really at rest. And and further, if we simulate star spots and get a sense of their magnetic fields, it can help us constrain surface magnetic field distributions of other stars. And for people who are interested in exoplanets, spots interfere in many ways with the detection with their detection. So the simplest way a spot can interfere with the exoplanet detection is by removing flux from a light curve. The other way which it can affect is it can affect the radial velocity of a star. I'll touch on this topic a little bit more later. And also, understanding star spots will help us understand better the sun as a star. So on the right, you have this video which shows how a spot rotating across the disk is affecting a spectral line. Right. So why do we need simulations? So the simple answer is that stars other than the sun are just too far away. So a lot of you here are observers, and you would know better than me what are the difficulties of resolving surface features on other stars. But here I've just so this is a paper by Rottenbacher et al. From 2017, and they have compared here three different surface imaging techniques of the same star. And so on the top you have interferometry, middle Doppler imaging, and the bottom you have light curve inversion. And what you see is that not only do not have a idea of the fine structure of spots or the fine scale surface distribution, the results generated by these methods don't seem to agree very well either. So I'll dive straight into what I've done. So there has been already a lot of discussion about what the Muram code is, what it does. So I'll skip that part. But just for a recap, we this is compressible MHD with radiative transfer and box in a star configuration, which means we're just interested in the top few megameters of the star. So this is my initial condition. So Tanavir, who starts with a hydrodynamic simulation and puts in very infinitesimally small magnetic fields, what I do instead is so on the left you have here so the grayscale map is the bolometric intensity before there is any magnetic field, and then once my hydrodynamic simulation has sort of stabilized, I put in a magnetic flux tube. So this is the BZ component of the flux tube. So you can see strong fields near the lower boundary and the flux tube fanning out as we reach the photosphere. And so this is the initial condition for the magnetic field. My boxes are also a little bit deeper than Tanavir's. And then I let this evolve with time. And what you see is so now the spot has formed. If you look carefully, you can also see that the depressed optical surface created by the spot where it is located, you can see some umbral dots, and you can see that the flux tube is not entirely well, it has changed, and flux has leaked out to form other small scale structures. So this is how I do my simulations, and I'll so these are the results from my first paper. So first, before I computed complete star spots, I did simulations in the slab geometry, and this is a published paper. You can go look it up online. I have given so it's 2020 published in APJ. And so I'll just present the main results from the paper here. So there are a lot of different physics that are going on in each of the spectral types. I'll just focus on the most important and the most pertinent here. So one is, as you can see, as also Tanavi showed, that so if you look at the length scales at the x megameters, the x-axis, so although all the three stars have similar number of granules, their length scales are very different, which means the granule sizes are, in absolute terms, are the largest in the G star and they're smallest in the M star. And this is because your granule size is determined by the local pressure scale height, which in turn is governed by the surface gravity, which increases from G to M, and temperature, which decreases from G to M. And the more important result here is that if you look at the contrast, the G star spot is around 30% as bright. Look at the G star umbra. It's at, it's nearly 30% as bright as the quiet star surrounding it. Whereas if you go to the M star, if you look at the relative intensity of the umbra, that is 70%. So relatively, the G star spot is much cooler on relative terms compared to its surrounding photosphere. So hotter the star, higher is the spot contrast. And I'll jump quickly to how it compares to observation. So we not only did we look at star spot temperature, we could also measure magnetic field strength in the spots. So on the top, you have spot temperature contrast. So this is on the y-axis, you have T photosphere minus T spot. On the x-axis, T photosphere. The green line here has been taken from a review paper where this is a compilation of star spot temperatures measured with a wide array of techniques. So starting from light curve inversions, Doppler imaging to molecular band modeling. So this is a fit to what the observers say about star spot contrast. And the red and the blue points are generated from my simulations. So the blue points are temperature contrast between the photosphere at tau equal to 1 and the spot at tau equal to 0.01, while the red is the both of them are at tau equal to 1. So what you can see is that, well, one, our spot contrast at the photosphere is a little bit lower than what you see in observations, but nonetheless, the basic trend has been reproduced very well here. So as you go to hotter stars, you see relatively colder spots, and this is seen both in our observations and simulations. Now, if you look at the lower panel, this is the magnetic field strength measured in the spots. So now I must warn you that magnetic field strengths of individual spots and other stars have not yet been measured, but what people have measured are the average field strengths of on stellar surfaces. So the dashed line here is representative of the average field strength measured on different stars, while here again the red and the blue points are what you get from my simulations. And what I want to convey to you here is that our simulated magnetic field strengths are in range of the magnetic field strengths that you see on other stars. Now I'll go into a little bit of the physics. That is, I'll try and explain why is it that you see such a sharp dependence of spot temperature with spectral type. So why is a spot dark at all? The simple answer to that is, so on the sun you have strong vertical magnetic fields. They inhibit convection, which means the heat that would have otherwise come up is not being transported to the surface. This makes it cooler. And also what happens simultaneously, that as it becomes cooler, there's a drop in the opacity, it radiates even better, and then what you have is an area with low temperature. So that is the basic mechanism of why a spot is cold. So now let's look at what happens with different spectral types. So this is a vertical cut which shows the radiative flux percent. So 100 or yellow means that the energy is transported entirely by radiation. One or blue means the energy is being transported mostly by convection. So this is a vertical cut through the spectral types G, K, and M. The red in boundaries indicate where the spot lies, and anything outside red is the quiet star. So what you see here is that, so, and by the way, the wiggly lines that you see, those are the pressure scale height. So 0 is the surface, and -1 is, so 1 pressure scale height above the surface, and so +1 would be 1 pressure scale height below the surface. So what you see here, let's look at, so just pay attention to my cursor here. So what you see here is that on the sun, for example, on the G25 star, your transition from convective energy transport to radiative energy transport takes place within a pressure scale height. So yellow, so blue to yellow, just one pressure scale height. And if you look at what is happening in the M star, this is spread out. The same change is spread out over multiple pressure scale heights here, almost 2.5 pressure scale heights. So the basic idea is that in cooler M stars, your radiative processes are playing a non-trivial role in the energy transport even below the photosphere. And so your magnetic fields are less coupled with the energy transport processes in cooler M stars. So yes, magnetic fields are still affecting your contrast, but not as much as on a hotter star like the sun. And this is again because the way your energy is transported, uh, the balance between radiation and convective energy transport is different on different spectral types. So just to recap, so this was my first paper of my PhD. Hotter stars have relatively cooler spots. The magnetic field in the umbra is in the 3 to 4.5 kilogauss range for all of the spectral types. We don't see a wide variation in the umbral field strength. And I also provided physical explanations for this. And if you want to learn more, you can go look up the paper online. So now this, as you might have noticed in the previous simulations, there was not a fully developed penumbra, and this was because of our boundary conditions. And but we must remember the sunspots are mostly penumbra, and the penumbra harbors flows in the kilometer per second. And it's often the case that in stellar physics, the penumbra is often forgotten. So if you look at the GIF again here, often people, when they think of a spot, they think of this uniform dark patch that is moving across a stellar surface. And I think it's time to sort of also emphasize now that that is not a spot. A spot is mostly the penumbra. And it is the penumbral properties that actually contribute more to the properties of a spot than an umbra, simply because the area of the penumbra is much larger. So and also because the penumbra is harboring flows in the kilometer per second range, so those of you who are interested in detecting exoplanets with precise RV measurements, this is very important because penumbral flows which might not be line of sight at the disk center, when they move to the disk towards the limb, these kilometer per second flows will have an effect on the line of sight velocities. So this led me to compute complete star spots. So these are complete star spots. So this is again G, K, and M. This time the simulations contain not just an umbra, but also an expansive penumbra for all three cases. And again, so what we find out is that, well, it's not only sunspots that have penumbra, but also K and M stars here have quite expansive penumbra, and the rate and the roughly the area ratio for umbra to penumbra is 1:4 in all of the cases. Another interesting thing I want you to notice is that if you look at the M star penumbra, so the circles here mark the boundaries of the umbra and penumbra. Right outside the circle which marks the boundary of the M star penumbra, you also have these elongated granules. This is not something that we see on the sun. So their contrast or their brightness is very similar to the white star surrounding them, but their shape is quite different. And this is again something that is very new and interesting. So here below I have plotted so I have taken azimuthal averages of the quantities, and these are, so for example, I by I quite and temperature with normalized radial distance. And the vertical lines show where your boundaries of the umbra and penumbra are. So black is for the G star, K is blue, M is for the red. And you find out again that the basic physics has not changed in this geometry. So your G star umbra has the lowest relative brightness, 0.2, M star is 0.65, and your penumbra has, well, the G star penumbra is 64% as bright, and your M star penumbra is almost 92% bright as the white star. And one thing you might remember from the previous plot where I compared my simulation results with observations is that at the tau equal to 1 level, I was getting spots that are too bright. But we see here in our complete star spot simulations that we actually get very good agreement, at least with the sunspot observations, that G star umbra is 20% as bright, and this is what has been consistently seen in observations. On the right, you see the temperature. I just want to, so the temperature reflects what you see in the intensity. I want to point out just something very interesting. If you look at zero, if you look at this point, the coolest part of the sunspot is actually colder than the M spot umbra, and I find this quite interesting. And here you're seeing the magnetic field. So this is B vertical for G, K, and M star. And again, below you have the azimuthal averages. And what you see again is, so the G, K, and M star, they're all, again, they have very not too different average field strengths. So G star has 3 kilogauss, M star 3.5. And so this is also, again, the basic physics does not really change from the slab to this geometry, but we just get more details, and this is very reassuring. And here you see the inclination. So in the field strength, so the inclination in the umbra is, the fields are almost vertical. As you go out to the penumbra, your fields become more horizontal. So I just want to point out here something is that, so our inclination for the penumbra is a little more than what we get on the sun, and this is because, so I am sort of aiding the formation of a penumbra by making my field lines a little bit more horizontal at the top boundary, and this makes our inclination angle a little steeper at the penumbra for all the stars, and we get stronger horizontal fields than what we expect. But other than that, the BZ matches quite well with solar observations. So this is again the Evershed flow. So by V radial, I mean radially outward. So blue means radially away, red means coming in. And again, we see all of the spots have Evershed flows. If you look at the radial azimuthal averages again, so the the G star has the strongest flows, and the M star has the weakest flows. The G star average Evershed flow is around 3 kilometers per second in the entire penumbra. This is again what is seen in observations. So although the flows become progressively, the Evershed flow becomes progressively slower from the G to the M star, what you see is that in all of the cases locally, you have flows that are supersonic. So both for the K and the M star. So just to summarize, so we have done complete sunspot simulations. Our complete sunspot simulations match well with observations. Our core findings do not change with change in setup. And we see that star spots, like sunspots, also have penumbra that harbor outward flows in the kilometer per second range. And we find exciting new physics in the M star umbra. Now we are also simulating, I've also simulated some spectral lines. So here I'm showing you the Hinode pair 630.2 nanometer lines. And so here what you see is, for example, on the top, the M star, umbra, penumbra, plage, and Quaeston. On the left, you have the I by I Quaeston continuum. On the right, you have the Stokes V. And what you see is that, for example, if you look at the umbra, it shows a wider splitting because it has stronger field strengths, and you see only the two components because the field is mostly vertical, whereas in the penumbra you see all the three components of the splitting. You also see changes in the line depth between the quiet star and the umbra because of changes in temperature gradients. And here you have, on the lower panel, you have the same, the V by I continuum, and you have the I by I continuum for the G star. This is in the visible, and again you see three splittings for the umbra. You see mostly the central bulge for the penumbra because your field is horizontal, and you again see a change in the line strength based on where you have simulated your spectral lines. And this is again in the titanium 1 line, and this might be important for some of you who are uh, working with instrumentations or observations, because these sort of synthetic spectral lines can actually help you constrain your degree of polarization, Zeeman broadening, and line strength for different spectral types. So I'll just want to show you something very interesting here, is that if you look at the titanium 1 line for the sun, because it's such a hot star, the titanium 1 doesn't really form at all in the quiet star, but it forms mostly in the spot. And in this can be very useful for solar-like, studying spots and solar-like stars, because your titanium 1 line would form only then in spots. And if you look at the M star, you see you see a change in that. Your titanium 1 line is actually much stronger in the quiet star, and in the umbra it's a little bit weaker because the titanium 1 in the umbra is forming titanium oxide molecules, and which is why the line is weakening. And so I'm also now combining these. So I'll quickly skip this slide. I'm also combining this spectral lines, creating disk integrated spectral lines to study the effect of radial velocity of spots on stars. And so what I've done here is, so this is a simulated radial velocity. So this is a spot that is moving along the equator, and I've studied different filling factors and different rotations. So what you have here is a spot that is 1% and 5% for a 3 kilometer per second star rotating at 3 kilometer per second, and then you have 1 and 5% for 1 kilometer per second. And if you look at the left plot, what you see is that there are two things that affect the radial velocity impact of a spot. One is the rotational speed, and one is the filling factor. And this is kind of it's intuitive and it makes sense. On the right, I did an interesting experiment. If you focus if you focus on the black line, what I did is this is a star that is without any rotation. So this is 0 kilometer per second, and you can see that how much of an effect simply having rotation will create on the radial velocity. So this is also work in progress, and I hope to extend it to other stars and with different spot configurations. So I'll now thank you for your attention. I've given you my email ID in case you have questions and you don't find the time to ask it here.
Thank you, Tanvir. That was a really interesting talk. Do we have any questions for this talk?
It's not Tanvir, Moira.
Oh, sorry. I plead great age and insanity, and it's too early in the morning. Do we have any questions? Yvonne.
Hi, Mayukh. That was great, really interesting, and great to see circular spots. That's really exciting. Was I dreaming? Was I imagining it that the M-star spots, the umbra, looked really, really featureless in intensity, but not necessarily in velocity and magnetic field?
Yeah, well, so the umbra is featureless in the M-star. That is a good observation. So this is because what we suspect is that the radiation, because the radiative processes play a greater role in the M-star atmosphere, it washes away all the features, and you don't really have any umbral dots. And I think you will also see that in the magnetic field strength. So if you look at the magnetic field of the G-star umbra, you have a lot of these tiny dots, which you do not really have in the M-star. So I think both the M-star umbra and the M-star intensity and the M-star magnetic field and intensity are kind of featureless, and there are physical reasons, and I think that is because, yeah, the radiation is basically washing out all the non-uniformities.
Can I say something to that?
Yes.
Let me hear. Yeah, so I think, Yvonne, you did notice correctly that there are structures in the velocity, for example, but that's because oscillations, for example, are there, and they're pretty strong in the M-star. We don't know if this is because the simulation hasn't completely settled down yet, or if this is something that is really there. And the radiation argument is completely correct. That's what kills all the structure in the temperature, but it can still leave structure in magnetic field and certainly in velocity.
Mm-hmm. Thank you.
I see there's a question from Oleg.
Yes, thank you. Very, very good talk. Very interesting to see this sophisticated numerical simulations. I have a question about the temperature pressure structure within the magnetized regions, let's say penumbra. Are you able to verify that in the magnetic regions, this structure is mimicking or is similar to the quiet star with a lower temperature, because this was a key assumption, this still is a key assumption in many stellar studies. It would be really interesting to check that using your simulations.
So in my first paper, I actually have vertical cuts of the temperature at different depths. And no, we do not find that inside the spot the temperatures. So one, this temperature structure is quite different. So I think if I understand your question correctly, you're asking if I just reduce the temperature of the quiet star, I gave the same temperature profile as what I would get in a spot.
Exactly.
Yeah, so that so that is an interesting study, and I haven't actually done that. So what I could do in theory is look at the G star umbral temperature profile and compare it to the M quiet star umbral profile and see
Exactly.
similar.
Please do
Yeah.
that. That would be very useful for stellar people.
Yeah, so I haven't done that explicitly, so I have to check that.
Are there any other questions? I have a little question as well. I was fascinated by your comments about the impact this might have on the radial velocity studies. But I was finding it hard to put the velocities you had in your spots and in your penumbrae in the context of the typical convective velocities for those stars. So could you give me an idea of how it compares?
Yeah, right. So your typical convective blue shift of a star. So if you integrate a spectral line over all disk positions, you would get a 300 to 400 meter per second net convective blue shift without the presence of any magnetic fields. And so we are synthesizing spectral lines at different disk positions and disk integrating them, and it's sort of difficult to quantify exactly how much one spot. Well, I haven't done an experiment yet, but I'll just tell you that the penumbral flows are in the kilometer per second range, and when they go to the edge near the limb, it's quite conceivable that their sine theta component will be in the range of a few hundred meter per second, and that is enough to affect your net convective blue shift, which is only a few hundred meter per second, for example, for solar-like stars.
I have a memory, and I might be wrong, but I have a memory of seeing somewhere that there's a large-scale inflow towards spots seen on the sun.
Yeah. So there's a large-scale inflow towards this, I think, and there's also outward flows like the Mote flow and all of it, but so we need bigger. So in these scales, we don't really see those flows. So one could also construct much larger boxes and study the flow systems that develop around the spot, and that would also, in theory, affect your radial velocities.
No, I think it's really interesting work. I think we probably have to stop the questions there.